lecture is going to be about 7.1 discrete and continuous variables. And the first thing we have to understand is discrete random variable, which means numbers of possible values. And a picture of the random variable consists of x, and each x represents the countable numbers of possible values. Like for instance, when we talk about flipping a coin and flipping a coin 4 times, we're trying to find the number of heads. So x1 stands for 0, x2 stands for 1, stands for 2, and so on, because 0 would stand for all of the coins tossed. So continuing with probability, the probability of PI must satisfy 2 requirements. And these 2 requirements are 1, probability P1 is a number between, PI is a number between 0 and 1. The second requirement is P1 and P2 and all the probabilities must add up to 1. To find the probability of any event is by adding the probabilities Pi of the particular values xi that make up the event. Michael!
Oh, wait.
Okay, since some of the students in our class are falling asleep, I decided to assign us a problem to do with our partners. So the following examples of probability is if 15% has A's and D's and 30% of them have B's and C's, 10% of the class has F's, and A represents 4. So the letter grade is 0 is an F, 1 is a B, 2 is a C, and so on. So the probability is 0.10, 0.15, 0.30 is from the percentage of the class, the percentage of what the letter grade the student gets. So the question is, what is the probability that a student got a B or better? So in groups, you guys should work on this.
This is so dumb.
I know, I'm not going to even do this problem. Don't even understand it.
Since I see that most of the groups are struggling with this problem, I'll be solving it on the board. So since the grade since we're trying to find the number of students that got a B or better, B represents 3 and a grade letter of an A represents 4. So since it's B or better, we're trying to find grade 3 or 4. And in order to do that, we find the probability of grade 3 or 4 equals the probability of x equals 3 plus the probability of x equals 4. And from the information given on the chart, we see that the probability of getting a grade letter of B in the class is 30%. And the probability of getting an A in the class is 15%. So we add up the total of the 2 probabilities and we get a total of 0.45. The height of each bar shows the probability of the outcome and its base. Because the height are probabilities, they add to 1. As the histogram have the same width, as you can see. So the areas of the bars also display the assignment of probabilities to outcomes. Think of these histograms as idealized pictures of the results of the very many trials. Coins is a very important concept, and so we will be doing an example of tossing coins. So, for example, we need to find the probability of the number of heads in 4 tosses of a coin. And for this problem, you have to make reasonable assumptions. So the first reasonable assumption is the coin is balanced. So each toss is equally likely to give heads or tails. The second assumption is that the coin has no memory, so tosses are independent. So, Michael and Julie, you guys and I will assign you a quarter, and you guys will do this experiment yourself and record down all of the results you guys get. The outcome of 4 tosses is a sequence of heads and tails, such as heads, tails, tails, and heads. There are 16 possible outcomes in all. The multiplication rule for independent events tell us that, for example, the possibility of getting heads, tails, and heads is 1/2, which is the possibility of getting a head, and 1/2 again for the possibility of getting tails, and so on. And if we multiply that, we will end up getting 1/16. So that is where we get each of the 16 possible outcomes similarly to the probability of 1/16. The number of heads x has possible values of 0, 1, 2, 3, and 4. 0 represents the number of 0 heads. 1 represents the number of having only 1 head in 4 tosses. So the possibility of having 0 heads is 1/16. The probability of having 1 head out of 4 tosses is 4/16, and so on. Since I have finished covering discrete random variables, I will move on to continuous random variables. When we use random digits to select digits from 0 to 9, the result is a discrete random variable. The probability model assigns probability 1 to 10, 1 out of 10 to each of the 10 possible outcomes. Suppose that we want to choose a number at random between 0 and 1. Allow any number between 0 and 1 as the outcome. Software random number generators will do this. The sample space is now an entire interval of numbers. S can equal to all numbers such that 0 is less than x and x is less than 1. A spinner can generate the numbers between 0 to 1. So how can we assign the probabilities to such events as 0.3 is less than x and x is less than 0.7? So since many of you guys are struggling with the examples I give, I will demonstrate how we can solve this problem. We cannot assign probabilities to each individual value of x and sum because there are infinitely many possible values. Instead, we use a new way of assigning probabilities directly to events as areas under a density curve. Any density curve has an area of exactly 1 underneath it, corresponding to a total probability of 1. Uniform distribution is the result of many trials that are represented by the density curve. The probability that the random number generator produces a number x is between 0.3, and 0.7. The probability of 0.3 is less than x and x is less than 0.7 is equal to 4. Since the answer is 0.4, the probability of any interval of outcomes is just the length of the interval. Similarly, the probability of x is less than 0.5 is equal to 0.5, and the probability of x is greater than 0.8 is 0.2. In these diagrams, you can see the outcomes of the results. Continuous random variable takes all places in an interval of numbers. The probability distribution of x is described by a density curve. The probability of any event is the area under the density curve and above the values of x that make up the event. All continuous probability distribution assigns probability 0 to 1 to every individual outcome. Like in earlier chapters, we will be using this formula z equals x minus the mu over the standard deviation. The standard variable is the standard normal random variable having the distribution n is 0 and 1.
In this section, we will elaborate on the distribution of random variables and focus on mean, variance, and the law of large numbers. Typically, we see mean as x bar or mu. In this section, we will be using the notation mu sub x. The sub x helps us distinguish one random variable from another. In the following example, we will be dealing with one random variable, so we will just use mu sub x. Let's say you play the lottery and you want to know the average payoff for buying a lot of tickets, and one ticket is $1. And if your number is picked, you win $500. Here's the probability distribution for winning and losing. In order to find the average payoff, we need to multiply each possible value by its probabilities, then add all the products. So the formula is mu sub x equals x1 times p1 plus x2 times p2 and so forth. In this example, we only need to go up to x2 and p2. x1 is $0, p1 is 0.999, x2 is $500, and p2 is 0.001. The sum of these two products is 50 cents, and this money amount is the mean of the random variable. In order to find the mean for a continuous random variable, its mean is described by a density curve. Now, moving on to the variance of a discrete random variable, an exact formula exists, and this is the formula. Variance is basically standard deviation squared, and in this case we will be using the notation with sub x, and the sub x helps us distinguish one random variable from another. So the formula is variance equals x1 minus mu sub x squared times p1 plus x2 minus mu sub x squared times p2 and so forth. Now for the following example, we have the probability distribution of iPods. Now in order to find the variance, the mean must be either given or found. In this case it is already found, and it is 5,000 iPods. So all we have to do is plug in the mean of the random variable for how many ever values there are. In this case, there are 4 values. So x1 would be 1,000, mu sub x would be 5,000, and we need to square this and multiply by p1, which is 0.1. then we need to add this to x2 minus mu sub x, which is 3,000 minus 5,000 squared, times p2, which is 0.3, and we need to add this to 5,000 minus 5,000 squared times p3, which is 0.4, plus the last value, which is 10,000 minus 5,000 squared times 0.2. When you solve for this, you will get 7,800,000. So this is the variance of the random variable. In order to find the standard deviation, we have to square root this number. Which is equal to 2,792.8. This is the measure of how variable the number of iPods sold is. Lastly, we have the law of large numbers. Let's say we were to estimate the mean height of teens. We would have to take an SRS and use the sample mean, x bar, to estimate the unknown population mean, mu. As the number of teens increases, the sample mean, x bar, will approach the population mean, mu. So eventually, we will estimate the mean height of all teens very accurately.